So we're going to look at the atomic orbital energy level diagram. The energy is going to increase as we go up. And so the lowest energy for the electron is this, which we call the 1s or the 100. This is for quantum mechanics. We're just comparing quantum mechanics to the Bohr model. And so the quantum mechanical model will have the same energy as the Bohr. And so this would be like the first orbit in the Bohr model. Here. This would be the n equals 1 orbit. And so it's the same energy. This is why the Bohr model was successful for some time before being abandoned. But we don't call this an orbit. You know what we call this in quantum mechanics?
Orbital.
Orbital. Okay. So this is the 1s orbital. We'll talk about the difference after I draw out the rest of this. And so the next allowed orbit in the Bohr model was the n equals 2. Well, the next allowed orbital is actually a total of 4 allowed orbitals with the same energy. We'll have the 2s orbital or the 200. 200 is this code n, so it's the same n as over here. N, and then this is supposed to be the same. Not sure if they're coming out the same, but LM 200. And then there's also the 2p, and the 2p is the what we call a sub-level or a subshell. And the 2p is going to consist of 3 orbitals. There's going to be the 2, 1, negative 1, the 2, 1, 0, and the 2, 1, 1. And you already saw the pattern here. The pattern is that there are n squared orbitals for a given n. And so here n is equal to 2. We have a total of 4 orbitals. Okay, then we go to the n equals 3. Now, there's going to be a smaller jump in energy. There's the biggest jump between 2 adjacent orbitals will be the 1 to 2, and the 2 to 3 jump is smaller. And this would correspond to the 3rd orbit, but in terms of quantum mechanics, this would correspond to a set of 3 subshells. And the 3 subshells would be, the electron could be in the 3s subshell, or the 300. The electron could be in the 3p subshell. The 3p subshell consists of 3 orbitals. The 3, 1, negative 1, the 3, 1, 0, and the 3, 1, positive 1. Or the electron could be in the 3d subshell. The 3d subshell contains 5 orbitals. And so the 3d are going to consist of the 3, 2, negative 2, the 3, 2, 1, the 3, 2, 0, the 3, 2, 1, and the 3, 2, 2.
For 3D, why is the 3, 2, 1 before 3, 2, 0 not negative, like 3, 2, negative 2?
Oops. It's negative 2, negative 1. The actual order doesn't matter because all these orbitals are the same energy. And so we have 3 subshells. Can you guess how many subshells are going to be in the n equals 4?
16.
Okay, now we have different jargon for this. They're going to be a total of 16 orbitals divided into how many subshells?
4.
4 subshells, right? And so we're going to have 16 total orbitals divided into 4 subshells. What are the subshells?
4s.
4s.
4p.
4p. How many 4p's are we going to have?
3.
3. And then
4d.
4d. 5 of those. And then 4f. How many 4f orbitals are there going to be?
7.
7, correct. How did you figure that out?
Each cell increases by 2.
Okay, so you see a pattern there that increased by 2.
Another way that it's 1, 3, 5, 7. It's kind of exponential.
Well, how about let's go to because we want to see a pattern here. We want to recognize a pattern. So that I don't want to draw out the whole thing. So let's say I'm going to jump to the n equals 15. The n equals 15 will have, well, actually, let's do an easier one. Let's go to n equals 10. N equals 10 is going to have a total number of how many orbitals? 100 orbitals divided into how many subshells? 10. What are the subshells?
10s, 10p, 10d.
So, yeah, so what we want to be able to do is we want to be able to go to any of these, n equals 10, and then be able to predict. There's going to be 100 orbitals. What are they?
10s,
The 10s,
10p,
the 10p,
10d,
10d,
10f.
10f.
What comes after that?
What's after f? I'm sorry? Well, we didn't get this far, but we're using a pattern to try to go beyond.
Well, it's going to be 9. I just don't know what subscript letter would have to be.
SPDF. Do you know where these letters come from?
I do not.
These letters come from the spectrum. You know, they're looking at the electronic spectrum, and one of the peaks was very sharp, and so they labeled it S for sharp peak in the spectrum. And then they have the biggest peak, a big peak, and then they called that the principal for P. And then they had this peak that was spread out. This peak that was spread out, they called diffuse. And so that's the origin of these here. And then we have F. And then it goes alphabetical after that.
Oh, then 10a.
Yeah. So A, B, C, D, E, F, G. So we're going to have the 10G. Now, how many orbitals are going to be in the 10G? Okay, you want to say 2 more than the previous one, but that means we have to get the previous one, and the previous one, and the previous one. So if I asked you how many orbitals are in the 10Z, then you'd have to go from the beginning to the end. Is there another pattern that we could use that we could just figure it out without having to do that?
2L plus 1.
Yeah, 2L plus 1. That's the other pattern that we could use. So F, 1, 2, 3, 4, 5, 6, 7, 8, 9. This would be the 10G. How many sublevels do we have so far? 5. So we need an additional 5 more. So after 10G would come 10H. Okay, we're going to do it a little differently now. If we look at the L's, we can figure it out. Because each sublevel will have a different L. So when we look at the first sublevel, L is equal to 1. When we look at the second, or 0, sorry, L is equal to 0. The second subshell or sublevel, the same thing, L is equal to 1. So the pattern goes, we have these 2L plus 1 orbitals. So if we know what the L is, then we can figure out how many orbitals. So for example, if I said L is equal to 20, how many orbitals? 21. So here we're going to have 2 times 0 plus 1, which gives us 0 orbitals. Those are the m values. What we can figure out are the m values from this. And we'll look at a pattern for the m values. M is equal to 0 here. L is equal to 0. Over here, how many orbitals do we have? We're going to have 2L plus 1, which is going to give us 3 orbitals. And when we look at those 3 orbitals, we're going to label those with different m values. And so each m value tells us which orbital it is in the subshell. So the m value is going to be -1, 0, and 1. And so that gives us 3 m values for 3 orbitals in this subshell here.
How do these look like in what do these?
We'll talk about what they look like shortly. Okay, when we have L equals 2, that's what we call a d orbital. And so L equals 1, we call a s orbital. I mean 0. L equals 1, we call a p orbital. L equals 2, we call a d orbital. There's going to be a total of 5 orbitals. And each orbital is going to be labeled by an m value. M is called the, there's different names we call it. L we call the angular momentum quantum number. M we call the magnetic quantum number. There's physics origins for these, which we aren't going to talk about. But this is going to vary from -2, -1, 0, 2, and plus. 1 and 2. I don't know. Mixed up. But do you see a pattern with the m values?
Yeah.
What's the pattern with the m values?
No, what we
They go from -L, right? This is -L to
plus
L. And so we take on all values from -L to +L, including 0. Here, the same thing here. This is -L to +L, going through 0. And this would be -L, which is the -0 to +0. It's only 0. And so when we go to F, it's 3 is an F orbital. L equals 3. And then what are the values for M here?
-3, -1, 0, 1, 2, 3.
Yeah. -3, -2, -1, 0, +1, +2, +3. And then we could label these orbitals with the quantum numbers, N, L, M. So this first one would be a 3, 3, -3. And so the first quantum number tells us the energy level. And so that's called the principal quantum number. The principal quantum number basically tells us the energy. The second quantum number tells us the subshell. And this is the F subshell. The F subshell, another way of thinking about it is these have different shape orbitals. Now, all these are allowed orbitals. And then the -3 tells us the orientation of that particular orbital, which is the M. And so this would be 3, 3, -2, 3, 3, -1, 3, 3, 0, 3, 3, 1, 3, 3, 2, 3, 3, 3. All right, so what we can do is this is going to be G. This is going to be 3G. Oh, 3G orbitals. 4G orbitals, sorry, 4G orbitals. G is an L equals 4. Actually, 10G, sorry, this is 10G orbitals. And then we have the 10H orbitals. So the first thing is, if we want to figure out how many orbitals are in the 10H subshell or sublevel, we have to figure out what number H corresponds to. So H is going to be what number? L. That's going to be 5. That's H. And if it's 5, how many orbitals are there going to be? Well, it's 2L plus 1. 2L plus 1 is 11. So did I write 11? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And what are they? What are they? Well, we need the M values. So the M values are going to vary from what to what?
-5.
Yeah, -5 to +5. -5 to +5. And so then we can list them out. So this first one's going to be a 10, 5, -5. And the last one's going to be a 10, 5, 5. And then just follow this sequence. So it's much more complicated because in the Bohr model, when an electron gets promoted to the 10th orbit here, that's it. It's just in the 10th orbit. And it's just orbiting around the nucleus with a pretty big orbit compared to the other orbits. In the quantum mechanical model, when an electron gets promoted to the 10th, it can occupy one of the 100 orbitals here. There are additional rules, depending on how it gets promoted. And so not all of these promotions are allowed. But there are a whole bunch of allowed orbitals in here. And so what we're going to do is we're going to take a look at these orbitals in more detail. So the first thing,
Alphabetically for the subshells, once you reach Z, what do you go to next? Would you go to AA?
AA, right? And then just on. It's going to get quite, because what's the highest energy orbital?
0.
Infinity. So they're going to be infinity squared allowed orbitals. And it's not infinitely far. It's going to converge up here. So we're going to have infinity here. Just like over here, these are going to start getting closer and closer, and then we're going to get to n equals infinity. N equals infinity for the hydrogen atom isn't so far away. It's not infinitely far away. It's just 2.179 times 10 to the minus 18 joules away.
This represents locations for electrons, right?
Right.
So wouldn't infinity orbitals mean infinity electrons as well?
No, it doesn't. These are all vacant. The hydrogen only has one electron. And so it just has a lot of different places it can go, a lot of different addresses it can be at.
The hydrogen atom in the Bohr model only works for the first orbital, so does the hydrogen atom correspond to the Bohr model?
The hydrogen atom, in one sense, corresponds to the Bohr. The picture is wrong, though. In the Bohr model, all these are orbits. But in reality, they aren't orbits. In reality, what we have are orbitals. And these orbitals are where the electron can reside, basically. These are the allowed energies and states for the electron. And so let me talk about this. The transition between the Bohr, because Bohr was no longer valid. The problem with Bohr is it couldn't explain multi-electron. And let's talk about multi-electron just briefly, and then we'll come back to this. So I need to make some room here. Bohr model could explain hydrogen, But the Bohr model couldn't explain anything with more than one electron, because what happens when we have more than one electron, the sublevels split. What I mean by splitting is they're no longer energetically degenerate. They don't have the same energy. In a one electron species like hydrogen, the 2s and the 2p have exactly the same energy. In a multi-electron species, this is single electron. The energy level diagram for a single electron species. It doesn't have to be hydrogen. It could be like helium plus. And so this would be hydrogen, helium plus, lithium 2 plus, etc. Helium plus is extremely unstable, but it would work. There would be some key differences, but it would work. Now, for multi-electron, let's look at the energy level diagram for multi-electron species. This is, what did I call it? Energy level diagram. And I called it the atomic orbital energy level diagram because we have lots of different energy level diagrams. This is the atomic orbital energy level diagram. And so for multi-electron species, what we see is that the sublevels are no longer energetically degenerate. And so when we go to the next energy level, n equals 2, the 2s and the 2p no longer have the same energy. The 2p are just slightly higher in energy than the 2s. And then it jumps up to the 3s. So we get to the 3s, and then the 3p are slightly higher in energy. And then it turns out the 3d are quite a bit higher in energy than the 3p. So the 3d are up here. And the 4s kind of sneaks in here and actually is lower in energy than the 3d. And so the sequence would go 4s to 3d, and then 4p is higher in energy. But where are the 4ds? The 4ds are way up here. And so what we have is this. We have a different grouping. And so this group, well, this 1s is by itself. So what we call this is the first shell or period. The 2s and the 2p, this would be the second shell or second period. The 3s and the 3p are going to be the third shell. And so in the third shell, there's no 3d. And so these are closely spaced orbitals in terms of energy. The 3d actually belong to the fourth shell here. And so this would be the fourth shell or fourth period. The 4d actually belong to the fifth shell. The fifth shell is going to look similar to the fourth shell. And so the fifth shell is going to consist of the 5s, the 4d, and then the 5p. But what about the 4f and the 5d and the 5f and the 5g? Where are those? Yeah, so what shells are those? In fact, that's kind of a curious question. What shell are the 5G? Do you think the 5G are going to be in the sixth shell or the seventh shell? We want to be able to predict this stuff, and we want to see if there's a pattern. And in fact, there is a pattern. And so let me talk about the pattern for this. When we get to multi-electron species, we can tell what orbitals are in the shell by making this kind of inverted pyramid. And so we start off with 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 5g, 6s, 6p, 6D, 6F, 6G, 6H. You see 7S, 7P, 7D, 7F, 7G, 7H, and then after 7H comes 7I. How many orbitals are in 7I subshell?
13.
Okay, that's good. We did 0, 1, 2, 3, 4, 5, 6. So you're right. 2 times 6 plus 1 is 13. Good. So we want to do these patterns so that we can figure things out without having to build it up from scratch each time. Now, we can figure out what orbitals are in the shell by doing this diagonal pattern. And so in this diagonal pattern, in the first shell, there's just one orbital. In the second shell, there's the 2s and then the 2p. This would be the second shell. Maybe I should do it like this. The 2s and the 3p. In the third shell, there's a 3s and then the 3p. So each shell begins with an s. I should do it here. Each shell begins with an s. And so the next shell is 4s, and then we curve around here, and it would go to 3d, 4p, and then we stop here because the new shell begins with s. And then the 5s, which would be the fifth shell is going to have 5s, 4d, 5p, and then stops at 6. So tell me what the sixth shell has.
6S,
6s,
6D, 4F,
4f first, 4f,
5D,
5d,
6P.
6p, stops. The seventh shell,
7S,
7s,
5F,
5f,
6D,
6d,
7P,
7p,
stop.
and then stops at 8s. So the 5f actually goes into the seventh shell. Where's the 5g at?
8th shell.
Eighth shell. Do you see that? And so we can build this up by shells. Over here was easy with single electron because single electron, each shell just has all the same orbitals here, like this. How about this? There's forbidden orbitals. Like, for example, you can't, there's constraints here. So, for example, take a look at L. What's the maximum L value that a sublevel can have? So when I look at this, when we look at the pattern of what's allowed, we'll see certain things. Like, for example, if I look at my L is equal to 1 here. Why don't I have an L equals 2? The reason I don't have an L equals 2 is it's forbidden for an N equals 2, but it's allowed for an N equals 3. And so there's another pattern here, and the pattern is this. We don't see a 1p. We don't see a 1p because that is not observed. It's not observed, and it also violates what we call the Schrodinger equation. The Schrodinger equation is the main equation of quantum mechanics. All these orbitals come from the Schrodinger equation. And so if we wanted to make a 1p, a 1d, a 1f, etc., all these are forbidden. All these are forbidden because they exceed the max L value. Well, what is the max L value? The max L value is n minus 1. We can't have an L that's greater than n minus 1. This is what the pattern is, and this is why we can add one more with each step here. And so there are other mathematical patterns, but basically this is what we want. We just want to be able to generate this. Okay, now what do the orbitals correspond to? The orbitals correspond to the energy and the shape. And this is the shape of something called the probability distribution. There are some key developments here in going from Bohr to quantum mechanics. Do you know what those key developments were? Probably two that we're going to worry about. One was de Broglie. Does anybody know what de Broglie's contribution to quantum mechanics is? De Broglie talked about wave-particle duality. Wave-particle duality. We see wave-particle duality with light. Light comes in little packets called photons, and a photon can be treated as a particle of light, although it doesn't have any mass. Well, electrons do have mass, and electrons are particles, physical particles, but they also can be treated like light because they have wave properties as well. We don't notice the wave properties of electron until certain things make it very apparent. And then the other thing that came about is Heisenberg. Heisenberg talked about the uncertainty principle. Have you heard of the uncertainty principle? Well, it's named after Heisenberg, the Heisenberg uncertainty principle. You know what the uncertainty principle is?
The 95% chance that it will be within the orbital.
Yeah, right. What Heisenberg said was there is a limit, a fundamental limit to precision. And let's just talk about it briefly here. Heisenberg said that there's going to be a fundamental limit in quantum mechanics. There's going to be a certain amount of error in this that you can't get rid of. And this error is going to be distributed between an error in the energy or momentum. Momentum is energy. It's technically Heisenberg said momentum. And so it's an error in the energy times the error in the position. So what Heisenberg said was you could know both of these with some error, or you can pinpoint one of these, but the other one will have more significant error. So in other words, we have to make a compromise. We either know the energy, and that means we don't know exactly where the electron is located, or we can know exactly where the electron is located, but we won't know what its energy is. And so the way it translates is this. If you have an atom here and you find an electron in this position in space, and you measure it, and so the electron's there, you shine a photon, the electron's here. But you don't know what energy that electron is. That could be a higher energy electron or it could be a lower energy electron. You just don't know. You just know it's here in space. Or we could know the energy, but then we aren't really going to be able to pinpoint its position. That doesn't mean we don't know anything about the electron. It depends on the energy of the electron. If it's a low energy electron, then the position most probably is close to the nucleus. If it's a higher energy electron, then it could be further from the nucleus. And so it's not totally unknown where the electron is. But we're going to have this. And so this brings us to this concept of orbitals here and the way we're going to visualize it. And so we'll do a comparison here between the orbit. The first orbit in the Bohr model is at 0.54 angstroms. in quantum mechanics, we have the first orbital. And the first orbital is going to be like this. It's going to have the same energy, minus 2.179 times 10 to the minus 18 joules. And so this will be, we're going to pinpoint the energy, minus 2.179 times 10 to the minus 18 joules. Same energy. But the difference is we don't know exactly where the electron is. In the Bohr model, we know the electron's orbiting at 0.54 angstroms. In the quantum mechanical model, it's like a bird. The electron's like a bird. And the bird's going to have this much energy. So the bird might be here, it might be here, here, here. And so if we take snapshots of this bird, then we're going to get a probability distribution like this, and we call this electron cloud. And we just measure the position of the electron at certain times. It's not that high energy of electron, so the probability it's going to be found far from the nucleus is very low. But there is probability it might make it out, but it's just low probability. And so we call this the 1s orbital. In Bohr, we call this the first orbit. In quantum, we call this the first orbital, or the 1s orbital, which is the first orbital. Now, there's a connection here between 0.54 angstroms. What is the most probable distance that the electron is from the nucleus? 0.54 angstroms. And how did we get that? And so let's take a look at the most probable distance. So again, this is called the electron cloud. And we're going to talk more about this, or the probability distribution. And this is due to the Heisenberg uncertainty principle. The greater the density of dots, the higher the probability. So what we're going to do is we're going to do two things here. We're going to divide the space around the nucleus into slices. These slices are like onion. It's like an onion, where we have the first shell, I guess you call it, and then the second, the third, the fourth. When we look at this, the volume of these slices actually isn't the same. So out of these that I've drawn, which one has the largest volume?
The first one.
It turns out the first one doesn't have the largest volume. The last one that I drew has the biggest volume, because I'm going to make these equal in thickness. And so the volume is interesting. If we start off with the center here, the lowest volume will be the first one. And then each successive one will have a larger volume. And so the volume increases like this. But if I look at the probability, which shell has the greatest probability? The one closest to the nucleus, because the electron doesn't get too far off. So in terms of probability, the highest probability is going to be right next to the nucleus, and then the probability is going to decrease as we go down. And so I'm going to ask you, which shell has the most dots? Is it going to be the first shell that has the most dots, or the last shell? It's not actually going to be the first shell, because I didn't really draw it accurately. It's not the first shell, because, although the way I drew it here, it is the first shell, but it isn't the first shell. Let me try to do this. I just got tired of drawing dots.
It will be the shell that's equal distance from the first to the last one. Because that has the most probable distance.
Yes, something like that. The last one's infinity. But the shell at a radius of infinity is going to be huge volume, but there's no dots. Or maybe one dot. And so we need a compromise. And what is the compromise? The compromise is here. This is called a distribution function. This really is a distribution function. And so basically it's going to peak. Where does it peak?
Right at the intersection?
Yeah, right at the intersection here. And so this shell will contain the most dots. This shell has the highest density of dots, but the volume is small. This shell has the highest volume, but the density of dots is very low. And so we have to maximize both functions. And maximizing both functions is going to occur at how many angstroms?
0.54.
0.54 angstroms. And so and this is why the energies are the same. The energies are the same because the effective distance of the electron from the nucleus is the same in the 1s orbital and the 1s orbit. I mean, the first orbit. It's not called 1s orbit, the first orbit. And so they have the same energy. Now, the wave properties, we'll talk about the wave properties, but let me talk about the 2p orbital. The 2p orbital, these are what we call wave functions. And the wave function is like this. And we usually use psi NLM. So this orbital here is the psi 100 wave function of the psi 100 orbital. And in terms of wave function, it looks like this. This is the nucleus here, right in the center. Now, when we do probability, we don't want any negative probability. So for probability, it's psi squared. Psi squared is the probability. So what we do with the wave function is we just square the wave function. This is psi, this is radius. And so if we square the wave function, well, it's just going to be like this. And this is psi squared, this is the radius. And so we can see the highest probability is right next to the nucleus. And so that's what's going to give us the most dots, right next to the nucleus. As we go further and further from the nucleus, then we're going to get fewer and fewer dots. And so the probability is radius right at the nucleus here. You can see it from psi squared. All right, that's the first allowed energy. Orbitals contain all the information for the electron. All the information is the probability distribution and the energy. Okay, the next allowed orbital will be the psi 200, or the 2s orbital. Now, when we take into account the wave properties of the electron, the psi 200 orbital looks like this. Do that great of a job here. This is what we call positive amplitude here. This is a positive amplitude. This is positive amplitude, but this other lobe is what we call, well, if it's not positive amplitude, it's going to be negative amplitude. Sometimes they color code this. You know, this might be red color coded for positive, blue color coded for negative. We don't have to color code this because we can easily see that's positive, that's negative. And what we do is when we do this probability, we square the wave function. So what we're going to do is we're going to square psi 200. When we square psi 200, what's it going to look like? It's going to look like this. This one is just going to grow bigger. However, what happens to this one? This one being squared is going to be positive rather than negative. And so we'll get a positive probability like this. But when we square something, we lose information. Whenever you square something, you lose what's called the phase. And therefore, when you take the square root, whenever you take the square root of something, like if you take the square root of 4, what is it?
Plus or minus 2.
Plus or minus 2. Well, which one is it? Was it plus 2 or was it minus 2 or was it plus 2 and minus 2?
It's possibly both.
It's possibly both. You don't know. And that's called phase information. Phase information is lost. And therefore, to not lose the phase information, we code these. And so this one will be coded positive. We might color it red. And this one will be coded negative. We might color it blue. And so people do all kinds of stuff to code these.
For the sign that was used with wave function, what's its name?
The sign that's used,
Just wave function.
the amplitude. You mean this?
No, the
Oh, this psi, PSI. Yeah, PSI, psi. It's a Greek letter. Psi. Okay, in order to not lose the information, we color code these. Sometimes, not all the time. You know, it depends on if we want to color code them or not color code them or whatever. And so what we end up with is a probability distribution that looks like this. And so we'll put the nucleus here, and we're going to have a probability out like this. It's going to have the greatest probability a little bit distant from the nucleus. And out like this. The distance of the electron here, the most probable distance of the electron in here is a little bit closer than 0.54 angstroms. But what we do is if we could spread the electron out over three-dimensional space, then the effective distance is actually the same. What is the effective distance? The effective distance is if that electron could be spread out over three-dimensional space like this, then the effective distance would be, you know what? Would be 0.54 angstroms. But what happens is the probability is concentrated in what we call this lobe and this lobe, and it's a little bit closer. And so this little bit closer but less volume is going to equal, if I spread the whole thing out over 3 dimensions like the S, it's going to give me the same effective distance. So if they both have the same effective distance, they're going to both have the same energy. And therefore, 2S, actually, this is, sorry. What am I doing? I jumped ahead. Sorry, I got to do this. This is for the 2P. 2P. The 2S is just a bigger version of this. So let me do this. We'll put the 2S here, just bigger version of the 1S. Except there's one large difference. Let me insert that here. The one large difference is it has two it has this little shoulder. Do you see that? So this would be psi. And this thing where this valley where it touches zero, that's called a node. And it's just one node. And so when we look at the probability distribution, it's going to look like this. Be psi squared. And when we look at the electron cloud, it's going to look like this, where the highest probability is going to be here. And then there's going to be a nodal region. The nodal region is going to be a place where there's zero probability, where the amplitude goes to zero. The amplitude goes to zero at the node, and then we have probability after the node here. And so there's going to be a blank shell in here, a hollow shell in here where there's no probability. This is called a node as well here. Sorry, so this is the 2-1-1 orbital. There are n-1 internal nodes. N-1 internal nodes. There's a node at infinity. The probability actually goes to zero at r equals infinity. So here's the internal node here. This node is called a planar node. This node here is called a spherical node. And so we have different names for the node. But anyway, let's talk about the wave and the wave functions. Here. And then what's that?
I'm looking at this. I have 2 node pages. I have more things to read and more than the slide.
So when we factor in the wave properties of the electrons, then the electrons are in an atom are like trapped in a box. We'll call the atom the box. And so one way of visualizing the wave properties is called particle in a box. But it's not just a particle, it's a particle that has wave properties. And so another way of thinking about it is it's a wave trapped in a box. So we call this the particle in a box. So the particle is going to have, particles are going to have wave and particle properties. So let's look at the wave properties of this particle. The lowest energy, I'm going to flip this. The lowest energy is if we have a wave like this. And so the other analogy for this is like an instrument, a stringed instrument. So if you pluck it, this would be the lowest frequency that you'd have. If you plug it harder, then we can get this wave here. And then the next one that's allowed would be another half wave in here. And so these would be the overtone here. And so here what we have is the n equals 1, where 1 is how many half waves you can get. Over here we have n equals 2. We fit 2 half waves in there. N equals 3. And so we're going to have this in multiples of half waves. And so we can see that the energy of a string is quantized. And so energy of a standing wave is quantized. And so if we put an electron in a small box, well, an atom is a small box. It's going to be clearly quantized because an electron in a small box will only have certain wavelengths that are allowed, because there's something called constructive and destructive interference of waves. And so if we look at an electron in an atom is like an electron in a box, or a particle in a box. And so if we put the proton here, and we have an electron here, and the electron has wave properties that we need to factor in, then what we have to do is we have to fit in a certain number of half wavelengths, so that what we end up getting is constructive interference. This would be constructive interference. However, if we don't fit in a number of half wavelengths, we get destructive interference, and that's forbidden. So for example, if I tried to put in 1 1/4 wavelengths in here, that would be forbidden. It wouldn't quite hit where I'm supposed to hit. And so the same thing. So this is allowed, and this is forbidden. Forbidden would be what we call or term destructive interference. And that is, the electron starts off here, and we don't get an integral number of half wavelengths in here. And so eventually what happens is, actually I didn't draw this quite right, but eventually what happens is the wave cancels itself out. And so destructive interference is the wave cancels, and it's forbidden. We're not going to have this particular half wavelength. This would be constructive. And the same thing, we can't fit a fraction of a half wavelength in here. It has to be a full half wavelength. We could see this in lots of things here. Well, for example, if we look at 2D scanning waves, are probably the easiest to see. You've probably seen this before. The 404 hertz, these are nodal regions here where there's no sand particles. Actually, no, the sand particles are in the nodes, sorry. The sand particles are in the nodes, and then we'll have amplitude at the other places. I wish I would have the sound. Should grab the other one where you can hear the pitch of the plate.
I don't imagine the pitch to be very pleasant.
See what the highest energy one they have. That's the highest energy. So the higher the energy, you can see we're going to get more and more nodes. There are more and more lobes, and it's going to get more and more complex. Let's take a look at the shapes of the orbitals here. So here we have the S. These are three-dimensional probability distributions, and these are what we call 95% boundaries. And so inside the boundary, there's a 95% chance of finding the electron. Outside the boundary, there's a 5% chance. And so this is the S. The P is going to have one node. The S, it depends. One S has no nodes, no internal nodes, except the node at infinity. 2S would have a node in there. 3S, 2 nodes. This would be the 2P with one node here. These are the Ds with 2 nodes here. And so we got to divide up the lobes. Most of these will look like 4-leaf clovers, but some of them look like, this looks like a P orbital with a hula hoop. These are the F, and so you're just slicing them with more nodes. We go on, and as we go on higher and higher.
Zero has no beautiful. Zero is just a
Yeah, we'll just get some, and this has to do with the wave properties of the electron. Now, when the electron's confined in a small box, the wave properties become important. Or when we get to higher and higher energies, it starts to look more continuous. So here it's clearly quantized. But when we go to higher and higher energies, so let's make a very tall box here. And down here at the low energies, we see it's going to be quite quantized, the next allowed energy here. But if we break this, let's just break this up here, and we go to very high energies, let's say I have 1,000 half wavelengths in here. Then I go to the next allowed energy. The next allowed energy is N equals what? 1,001. So do you think there's going to be a big difference in energy between 1,000 and 1,001? No. Okay, then let's keep going higher. Because the largest N we're allowed is infinity. So if we keep going higher and higher here, then we're going to get to, let's say, 1 trillion. Okay, what's the next allowed energy after 1 trillion? 1,000,000,001. Is there going to be much difference in energy between 1 trillion and 1 trillion and 1/2 wavelengths? No. And so pretty soon it's going to behave like a continuum. And so this is what, one of the things is this is why people say, well, quantum mechanics is confined to small. It's not really confined to small. Quantum mechanics is present in everything, whether it's big or small. It's just you don't notice it. You don't notice it unless the wavelength is significant compared to the size of the box. And so the wavelength of an electron at low energies is significant compared to the size of the atom. And so we notice it. It stands out here. But at high energies, it appears more of a continuum. And so this is why when we look at the energies here in the energy level diagram, it's significant. There's big jumps here at the low energy. But when we get to the high energy, we have to fit an infinite number of these lines in 2.179 times 10 to the minus 18 joules. Right? And so there's going to be an infinite number of lines. Pretty soon those lines have to be so close you can't even tell the difference up here. Okay, so this is for a small box. But other things behave like a continuum. So for example, tungsten. If you tried to make a tungsten vapor lamp, then what we get, this is, let's put this as visible light here. What we get are lines in the visible. I mean, there's going to be some kind of, let's just say light. We get a line spectrum. And so we aren't going to get white light. We're going to just get forbidden and allowed. And the reason is because in tungsten, the electrons are confined to the atom. And so in other words, electrons are confined to a small box. And so this would be something like this. However, when we look at tungsten filament, which is a solid piece of tungsten, then the electrons are free to move in that wire. And so they don't have to stick to one atom here. The electrons are mobile, and they can move from atom to atom. In other words, they're somewhat free within the confines of the metal. And so in this case, we get a continuous spectrum. It's a continuous spectrum because the electron has a huge box. And if the electron has a huge box, which is the piece of metal, then what we see is we don't see this situation where if the electron is confined to the atom, it's a very small box. In this case, the wavelength of the electron is small compared to the size of the piece of metal. The wavelength of the electron is significant compared to the size of the atom, but compared to the size of this chunk of metal, it's negligible. So what I'm going to have is I'm going to have 1 trillion half wavelengths in there, and 1 trillion and 1 is no problem. So I can excite the electron to 1 trillion and 1, trillion and 2, trillion and 3. Whereas over here, I have to excite the electron to the next higher state, which is going to be a more significant chunk. And so this is a particle in a small box. Whereas tungsten metal is a particle in a very large box. So the way I think about this, or the analogy that sometimes I use, is like if you have a killer whale in a small aquarium in San Diego, and it can't move that much, then what's going to happen is the kick of the tail. You know, one kick of the tail is going to be significant in the confines of the aquarium. But if that same killer whale were out in the free ocean, is one kick of the tail significant? No, they can do as many kicks as one, as few or as many. But over here in this small aquarium, one kick is significant. And so this is why quantum effects weren't noticed originally, because people weren't looking at single atoms, people were looking at larger systems. And for larger systems, it's not. Even a baseball is quantized, but a baseball can travel at any speed because the next half wavelength you can throw in there is marginally more energetic, in fact, negligibly. So anyway, this is it. And so what we're going to do is we're going to use this, and we'll let him come back to this a little bit. And so this is this is what we're going to do for this lab. Let me talk for a little bit more. A question comes up is, why is multi-electron split and single electron not split? And so why do we lose the degeneracy? So single electron 2s and 2p are the same because they both have the same effective distance, whatever that is. It's actually 4. 4 times R1, which is going to be about 2 angstroms. And so they both have the same effective distance, about 2 angstroms. So this is single electron. But in multi-electron, they're no longer degenerate. And so multi-electron, the 2s are going to be lower in energy than the 2p. I should say the 2p are going to be higher in energy than the 2s. And so why is that? It has to do with their probability distribution and the 1s. Over here, the 1s would be empty. So if I had an electron in the 2s, how do we show electrons in orbital energy level diagrams? Those arrows. So if I had an electron in the 2s, there's no electron in the 1s. So it doesn't matter if this electron goes in the 2s or the electron goes into the 2p. They're both going to have the same effective distance from the nucleus, and therefore the same energy. Over here, it makes a difference. If an electron goes in the 2s versus an electron in the 2p, when there's 2 electrons in the 1s. What happens is there's no shielding here because there's no other electrons. And so I say 4 here. In multi-electron, these inner electrons shield the outer electrons from the nuclear charge. In other words, these inner 1s electrons will block the 2s electrons from seeing the nuclear charge. And that's going to change their energy because the more positive charge they can see, the more stable it's going to be. And so if we put the nucleus here, and then we'll draw the 1s electrons. We can't pinpoint the 1s electrons, so we'll draw the electron cloud. Okay, this would be the electron cloud distribution for the 1s electron. Here. Now the 2s electron is going to have good probability that it's close to the nucleus. So the 2s electron, its electron cloud will be like this. And then there's going to be a node. I'm going to over-exaggerate the node, and then we're going to have probability out here. The highest probability is going to be right next to the nucleus. Like that. So let's draw the probabilities here. So we're going to have psi squared in r, distance from the nucleus. And so the 1s electron is going to have the highest probability here, that is close, nucleus, and then drop off. The 2s electron is going to have the highest probability here, right next to the nucleus, but it also has greater probability that it's farther from the nucleus as well. So it's going to drop off, hit a node, and then go like that. The 2p electron is going to look like this. It's going to have a low, maybe I'll do green. 2p. Yeah, it's going to have a lobe like this and a lobe like this. It's going to have the same effective distance as the 2s. And so 2p orbital is going to look like this. It's going to have a node right at the center and go out like this. Okay, now what we're going to do is we're going to look at, even though the 2s and the 2p have the same effective distance, they're different in terms of what we call penetration. In other words, here, the 2p orbitals are less penetrating than the 2s orbitals. And what that means is this. It means that the 1s are blocking, and the 1s are going to be more effective at blocking or shielding. These are the 1s electrons here. The 1s are going to be more effective at blocking the green from the nucleus than the red from the nucleus. Can you see that? And the reason is because the red ones are more penetrating, that is, they have higher probability than the green ones at being closer to the nucleus. The electrons, remember, we can't pinpoint them. They're somewhere around here. And so if we find an electron close to the nucleus, it could be a 1s, it could be a 2s, or it could be a 2p. But it's just, there's a greater probability that it's going to be a 2s than it is a 2p. And therefore, we say that the 2s orbitals are more penetrating. The 2p orbitals are less penetrating. So 2s orbital, more penetrating. If it's more penetrating, then we say it's less shielded. Then the 2p orbital. The 2p orbital is less penetrating than the 2s. And it's more shielded. And so this is what splits it out. In single electron, we don't have to worry about shielding. There's only one electron. There's no other electrons that are going to shield. In multi-electron, we have to worry about shielding and penetration. The 2s are more penetrating than the 2p. The 2p are more penetrating than the d's. Actually, there are no 2 d's. But we could do the same thing. The d's are going to be less penetrating than the p's. The f's are less penetrating than the d's, et cetera, et cetera. It goes on. So this is why we see splitting of subshells or sublevels. And so multi-electron, we have splitting of sublevels or subshells. And so this is the n equals 2 shell split up into 2 subshells. So what we're going to do in the end is we're just going to fill these orbitals with electrons. So what you need to do is you need to know the multi-electron atomic orbital energy level diagram. The multi-electron goes 1s, or the 100, the 2s, or the 200, and then the 2p, which are going to be slightly higher in energy due to shielding and penetration. And then we can write the quantum numbers. And then we're going to have the 3s, and then the 3p are going to be slightly higher in energy. But then we have to jump up to the next shell for the 4s, and then the 3d out over here, 3d, followed by the 4p, which is here. And so you should know this to the 4th period or the 4th shell. So 1st period, 2nd period, 4th. And okay, then we should know the difference between core electrons and valence electrons. Core electrons are excellent shielders. They're the inner shell electrons because we're going to have the greatest probability of being closest to the nucleus. The core electrons are going to shield, these would be the valence electrons. And so when we're dealing with shielding, we're looking at the core and the valence. And when we fill these, we'll just fill these with electrons using arrows. And so the first electron will go in the lowest energy. That would be hydrogen and then helium. And this would make the 1s shell full. Okay, then we'll go to lithium. Lithium will have 3 electrons. And we know the Pauli exclusion principle, which comes from quantum mechanics. And do you know the Pauli exclusion principle?
The spin.
Yeah. The spin is called, if it's arrows pointed up, we call that plus 1/2. If it's arrows pointed down, we call it minus 1/2. And that gives us 4 quantum numbers. And so the first 3 quantum numbers tell us which orbital. The last quantum number tells us the spin. And so this electron will be labeled 100 because it's in the 100 orbital plus 1/2. And the second electron will be 100 minus 1/2. And the Pauli exclusion principle says that no two electrons in the same atom can have the same set of 4 quantum numbers. So no two electrons in the same atom can have the same set of 4 quantum numbers. There are only two spin same set of 4 quantum numbers. There's only two spin states, plus 1/2 and minus 1/2. So there's nothing else, so we have to jump up to the next orbital. So this would be a 200 plus 1/2. That's lithium. And so we call that the valence electron. This would be the core. The core is whatever filled before, or inner shell electron. Valence would be outer shell electron. And then from lithium, we go to beryllium, and then boron. Boron would have to go to the next subshell, 2p, and then carbon, and then nitrogen. Okay, we fill these one at a time with parallel spin. What do we call that? We call that Hund's rule. Hund's rule tells us that we fill energetically degenerate orbitals one at a time because each of these 2p orbitals are the same energy. The difference is the orientation. So one of these 2p orbitals will be oriented on, let's say, the x-axis. Another of these 2p orbitals will be oriented on the y-axis, this. And the third 2p orbital will be oriented on the z-axis. Let's say this is the z going in and out. And so the only difference between these is not the energy, not the shape. The only difference is the orientation. So the m value tells us the number and the orientation of the orbitals. All right, once we go to, this would be nitrogen, then we go to oxygen, and then fluorine, and then neon. Neon fills the second shell. Helium fills the first shell. And then we'll go to sodium, etc. Fill those shells. And so what we're going to do today is we're going to take a look at the valence shell of the elements. Once we fill a shell like this, they're unreactive. And so the chemistry happens at the valence shell. That is, the outermost electrons interact. The inner electrons are pretty stable, and it's difficult to get them to react. Let me finish Hund's rule here. Hund's rule says fill energetically degenerate orbitals one at a time with parallel spin. I should say, we have a term for that, degenerate orbitals. Degenerate just means the same energy. Fill degenerate orbitals singly with parallel spin. Okay, once you do that, then you have to pair them up. Once you fill all of them, then we'll pair. It's Hund's rule. Off-bow principle says fill the lowest energy orbitals first. So off-bow, for ground state, fill lowest energy first. For excited state, you can put the electron in any orbital you want, depending on how much energy you use to excite it. So you can excite electrons to very high energy orbitals. So the sodium lamp there, this is sodium here. And the sodium lamp is we excite the electron at higher energy orbitals and then let it decay. Right, so we're looking at Lewis structures today. You guys remember how to do Lewis structures? So basically, we're going to look at the number of valence electrons The number of valence electrons is going to be the group number in Roman numeral. And so if we have boron, boron's in group Roman numeral 3, so there's going to be 3 valence electrons. Carbon is in group 4, there's going to be 4 valence electrons. We'll come back to this. Nitrogen has 5 valence electrons. Oxygen has 6. Fluorine's going to have 7. And then neon is filled shell, and that's going to have what we call an octet, 8 electrons. And so this goes to the same. Silicon would have 4 valence electrons. And so members of the same family will have germanium will have 4 electrons. Nitrogen, below nitrogen is phosphorus with 5 valence electrons. Below phosphorus is arsenic with 5 electrons. Oxygen, and then sulfur, and then selenium. Below fluorine is chlorine with 7, and then bromine, 7, and then neon, and then below neon would be argon with 8. It's xenon, etc. And so we're going to show these with dots. So we have our atom here. We're going to show 3 dots here. We usually show 3 dots separate. Carbon, we show 4 dots, singles like this. However, nitrogen, we're going to show 5 dots, 1 pair, 3 singles. Oxygen will show 2 pairs, 2 singles. Fluorine will show 3 pairs, 1 single. Fluorine and everything else in the family. And neon will just show 8. Neon fills the second shell. To fill the second shell, we'll need 8 electrons. To fill the third shell, we'll need 8 electrons. To fill the fourth shell, how many electrons do we need? To fill the fourth shell, we need 18 electrons to fill that. But even with the 18, we still, well, we'll talk about that more later. All right, well, let's take a break, and then we'll start the lab. All right, the first thing we're looking at is CHCl3, chloroform, or the other names for it, trichloromethane. You know, it's a methane with 3 chlorines, trichloromethane, common name chloroform. It's a liquid. It's not a gas, and it's quite dense. And it's a heavy liquid. It doesn't mix with water, it sinks to the bottom of water, so we form 2 layers. And you guys used chloroform before. Do you recall what you used it for?
No, is that not what I was thinking about?
I asked you to put a few drops, and then shake up the test tube. And what were you doing with the chloroform then?
Cleaning.
Not cleaning.
It was something with like a emulsifier.
Yeah, it was something, we're doing chemical reaction. We're doing redox reactions. We use the chloroform. Chloroform and water don't mix, and chloroform sinks to the bottom of water, so it forms a little liquid layer, or liquid bubble in the bottom of the test tube. Not an indicator. It's one of the properties. Chloroform, even though it kind of looks polar, it's pretty non-polar. And there's a rule, like dissolves like. And you're shaking it, hopefully you corked it up well, and hopefully it didn't spill out and get chloroform all over your hand. But we're doing an extraction. It's called a solvent extraction of
Halogens.
the halogens, right? Iodine, chlorine, and bromine love chloroform a lot more than water. And so that's how the extraction works. Well, anyway, we're going to look at the Lewis structure for chloroform. The first thing is, let's draw the energy level diagram for carbon. The energy level diagram for carbon, well, the first thing is, how many electrons does carbon have? Total. 6 electrons. So carbon has 6 electrons. Of those, how many are valence electrons? 6 total. Of these, we have 4 valence. All right, so let's draw the orbital energy level diagram. We start off with what orbital? The 1s or the 1? Another name for the 1s? 1, 0, 0. And then we go up to the 2s. Now, are the 2s and the 2p the same energy or different energies? Different. They're only the same energy when we have 1 electron species. So these are going to be slightly higher in energy than 2p. All right, so let's go ahead and fill these orbitals with electrons. And so we fill the lowest energy first, which is called the what principle? I just briefly mentioned the off-bow principle. Off-bow, we fill the lowest energy. And the off-bow principle works for the ground state. We could fill a higher energy. So, for example, the next electron could go in the 2p, but that wouldn't be a ground state. That would be what we call an excited state. So off-bow principle is just this. And then the next electron I put spin down, and that's because of what principle? Pauli exclusion principle. Because the first electron would be the 1, 0, 0, 1 half, and the second electron would be the 1, 0, 0, negative 1 half. How about the third electron? Could I put a third electron in the 1s orbital? No, because that would violate the Pauli. And therefore, the next electron has to go into the 2s or the 2p. And the 2s, because I want to adhere to the off-bow principle. Off-bow is fill the lowest energy first. Now, does it matter if it's spin up or spin down? It doesn't matter. Because spin up or spin down, there's no gravity here. There's no ground here. And so you're just out in space. So what if you're out in the middle of space, which direction's up, which direction's down? You don't know. And the atom doesn't know either. And so it doesn't matter, but by convention, we do spin up. This is by convention, but if you saw it spin down, then no big deal. Same thing, same energy. But once we put one spin up, the next one has to go spin down. So that takes care of 4 of the 6. And so I filled up my 2s sub-shell, and then I have to go to the 2p. Now the 2p, which one should I fill first? Should I fill the 2px, the 2py, or the 2pz? It doesn't matter. It doesn't matter. I can fill any of these. But we like to work left to right. Since we like to work left to right, I'll fill the... Yeah, but maybe in other countries they work right to left, so they might go the opposite. But anyway, here, we'll go here, and then we have one more, and this I'm going to put here. Does it matter if I put it in the second or the third? No, it doesn't matter. And rather than calling this the second and third, it's easier just to label these with the quantum numbers. So this is the 211, 210, 21, negative 1. And so we can either take the 210 or the 21, negative 1. The quantum numbers are very useful rather than saying the first one, the second one, the third one, because it doesn't matter. And so this is 1. But, you know, I could have picked the first and the third, or the second and the third, whatever. And then I'm done. So we have 2 core electrons, or inner shell electrons. So these are the inner shell, which we label the core. And so we have 2 core electrons. These core electrons do what to these outer electrons? They shield. Which one is going to be more effectively shielded? Or which ones are going to be less effectively shielded? In other words, which ones are more penetrating? The 2s are more penetrating, so that they're less effectively shielded. And the 2p are less penetrating, so they're more effectively shielded. And so And this is why they're higher in energy, because they're shielded more by these inner shell electrons. These are the outer shell electrons. The outer shell electrons we call the valence electrons. Now, the outer shell electrons are the valence. And how many valence electrons do we have? We have 4. But when we write carbon, carbon I should write as 1 pair, right? I should have 1 pair and 2 singles. But I don't write it as 1 pair and 2 singles. I write carbon as 4 singles. Why do I write carbon as 4 singles? It's got 1 pair and 2 singles. Does somebody know the answer to that? Okay, let me tell you, the answer to that is because of this. This is the normal ground state electron configuration. But sometimes things change because of things happen. And so what happens is this. When I form a bond, a covalent bond, and you probably know this, covalent bond, we end up sharing the electrons. This is why when we do formal charge versus oxidation state. Ionic bonds, there's no sharing, winner take all, right? So if I'm an oxidizer, I'm going to just try to strip all the electrons off here. However, when we form a covalent bond, we share. Now, is this electron available for sharing? No, it's already sharing this orbital. You see that? So the single electrons are available to pair. This one's already paired, so we can't share. So if I were to write it like this, how many bonds could I form? Well, how many electrons could be shared? These 2 could be shared. This is a lone pair. It's not going to be shared. You see that? Whereas if I write it like this, I have 4 singles that could be shared. But when I look at the energy level diagram, I don't have 4 singles. And so this is what happens. In order to maximize bonding, the more bonds we can form, the more stable. We're going to excite this. We're going to excite one of the electrons. In fact, we're going to take one of these s electrons and promote it to a p. And so we excite the electron here. And so this is the 2s, this is the 2p. And so what we're going to do is we're going to take that second electron and then bring it into the 2p. Now, what do I have? I have 4 singles. If I have 4 singles, how many bonds can I form? 4 bonds. If I can form bonds, that's better than forming 2 bonds, because the more bonds, the more stable, usually. And so here, this is correct, right? We got a pair and 2 singles, but when we're doing Lewis structures, we excite or promote that electron so that we end up with 4 singles. Now that we have 4 singles like this, now we can form 4 bonds. And what are the 4 bonds? Well, the 4 bonds is something like this. We're going to have hydrogen come in there. And how many valence electrons does hydrogen have? 1. And so hydrogen can come in here and bond. Here, in other words, it can share its electron. I'm going to flip it upside down, but it doesn't matter. Upside down, right side up, there's no such thing in space. So hydrogen comes here and shares. That's 1 bond. And then what comes next? Chlorine. Chlorine can come in here. Now, let's take a look. Hydrogen's energy level diagram. Now, carbon has how many protons? 6 protons. Okay. Now, if you're a 1s electron, you're going to see +6. You're going to see the full charge. And so if I'm a 1s electron, I see a full +6 charge. And so I have +6 in the nucleus, and here's a 1s electron. It is not shielded. Well, sometimes it's shielded. The same cell electron can once in a while go in front, but the shielding is not as effective. And so a 1s electron is not really effectively shielded by the second 1s electron, but it can be. So it's close to +6, not exactly. And so if we're a 1s electron, we see +6. If you're a 2s electron, are you going to see +6? You're going to see something less than +6, right? It's going to go down. If you're 2p, you see even less of that +6. That's shielding. That's what we call Z effective. So this is Z effective, which is going to be less. And so Z is going to be greater than Z effective for the 2S. And then when we compare it to the 2P, it's going to be even less. So this is Z effective. I'm writing Z, E, F, F. Read that. All right, so when I draw hydrogens, I want to draw hydrogen's atomic orbital energy level diagram. Hydrogen has one valence electron. Now, in terms of energy goes, the 1s orbital in hydrogen is a lot bigger or a lot smaller, or the same exact size as carbon. So, in other words, does it make a difference if I have +1 versus +6? So this 1s orbital sees a +6 charge. This 1s orbital sees a +1 charge. Does it make a difference? Yeah, it makes a huge difference. Which one is going to have a stronger attraction? +6. And that means this 1s electron in hydrogen is actually going to be further away because it's not going to be pulled in. And so in other words, the 1s orbital on hydrogen is bigger. Does that mean hydrogen is a bigger atom than carbon? No, hydrogen is smaller. So how can it be smaller if the 1s orbital is so much bigger?
The bigger the amount of protons it makes it smaller, and,
Yeah.
and it creates a smaller distance before electrons.
Exactly, that's exactly right. But overall, which one's bigger, hydrogen or carbon? Carbon's bigger overall. Why? Yeah, it has more electrons. It has another shell, and that other shell is going to be quite a bit shielded from the charge here, and so it's going to be a lot bigger. Okay, if it's a bigger orbital, is it lower in energy or higher in energy? It's higher in energy. So the 1s orbital on carbon is going to be lower in energy than the 1s orbital on hydrogen. Hydrogen's 1s orbital is higher in energy and bigger. But anyway, this is it. And I'm going to flip this one upside down here. I'm going to flip this one upside down so that it can pair up over here. And so that means carbon can pair up in this 1s orbital here, like so. And so here they're sharing. This is looking at it from carbon's perspective. From carbon's perspective, hydrogen's coming in here and sharing. And from hydrogen's perspective, carbon's coming in here and sharing. Do you see that? Look at that. All right, now let's go to chlorine. Chlorine has 7 valence electrons, so we write 3 pairs, and 1 single. Chlorine has altogether how many electrons? 17? Okay, so let's start this off. Now the 1s orbital on chlorine, chlorine has 17 electrons, and how many protons? 17 protons. So we're going to have plus 17 in the nucleus. What's that going to do to the 1s orbital? It's going to be really small. So the 1s orbital is going to be a lot smaller in chlorine than it is in carbon. But chlorine ultimately is going to be bigger. And that's because it has another shell of electrons. So for chlorine, we'll do this. The 1s orbital should be lower down and smaller. So this would be the 1s orbital, should be lower down than carbon and smaller. And then we'll put in 2 electrons here. So we have 15 more to go. And so what comes next after the 1s? 2s. And then the 2p. So that the 1s takes care of 2 electrons, and then we have the 2s and the 2p. These are going to be filled, and so that takes care of another 8 electrons. which is going to give me 10 electrons total. And then I have 7 more. And those 7 more are going to go into the next shell. The next shell will be 3s.
Yes.
Yeah. 3s. And then what? Not the 3D. That's the fourth shell. The fourth shell would be 3D. It's going to be 3p. And actually, that's the end of the shell. So to fill up the first shell takes 2 electrons. To fill up the second shell takes 8 electrons. To fill up the third shell only takes 8 electrons. You'd expect it to take up more electrons, but it doesn't. To fill up the fourth shell takes 18 electrons. And so we're going to fill up the third shell here. And we end up with this. We end up with 3 pairs and 1 single. And that's all we can do because there's no more room. So 3 lone pairs, 1 single. And who's going to come in over here? Well, who's going to come in over here? Actually, I need to flip this spin down, sorry. So for chlorine, I'm going to put this spin down like this. And then who's going to come in here? Carbon. Carbon's going to come in here and share its electron here. I should probably have thought of it. Over here, chlorine's going to come in here and share its electron here.
Mr. Shabbat, is there a way to tell if the electron is up or down spin?
There is, if you put it in a magnet. If you put it in a magnet, then all of a sudden it matters. Whether it's the same, like in the Earth's magnetic field, you can tell. But if there's no magnet, then you can't. And so what we do is we shoot them. The way they figured out the plus and minus 1/2, the plus and minus 1/2, the 1/2 comes from the Schrodinger equation. The actual number comes out to 1/2. But the way they could tell that electrons had 2 spins is they shot silver atoms through a magnet. And then half the silver atoms went this way, the other half went that way, depending on the magnetic orientation of the electron. Okay, so what we're going to have is we have still 2 more bonds that are here. And so another chlorine is going to come in here, which will look identical to this, and a third chlorine comes in here. And so we can get 4 bonds to this carbon, but we had to promote it, right? Up here. The next thing is there's something funny about the bond angles. There's going to be an inconsistency of the bond angle. So when I look at the chlorine, carbon, chlorine bond, we expect it to be 90 degrees because each of these p orbitals, this would be, let's say, the px, this would be the py, and the pz. Each of these are orthogonal to one another. They're 90 degrees. And so if they're 90 degrees, then we would expect them to be 90 degrees. This is expected to be 90 degrees because of the p orbitals. But it turns out they are not 90 degrees. The observed angle here is 109.5 degrees, or 109.48 degrees, or something like that. This is rounded to 109.5, or 109. If I want to round this to 3 sig figs, I round it to 109, not 110. Because I don't want a domino rounding.
19.
Yeah, where does that come from? And also, the shape. Do you know what the shape of this is? Tetrahedral. The shape of chloroform is tetrahedral. And not what you'd expect based on that. And so there's one final thing that happens here. The one final thing that happens is we need to minimize repulsion. Minimizing repulsions can lead to what's called hybridization of atomic orbitals. So let's look at the 2s, and then let's look at the 3,2p's. What we do here is we hybridize these, and so we create a hybrid. When you create a hybrid, we're creating some kind of mix, some kind of average of these. And so what we're going to do is we're going to take our S and 3 of the P's, and we're going to create new hybrid orbitals. These new hybrid orbitals, and these are hybrid atomic orbitals, are going to be closer in energy to the P's. And so we're going to get 4 equivalent orbitals like this. Each of these orbitals are going to be exactly the same, and they're going to consist of 1 part S and 3 parts P. So we're going to label this 1 part S, 3 parts P is called an sp3. And so that is 1/4 S, 3/4 P. And each of these are going to be sp3, sp3, and sp3. So if I take an S and mix it with a P, I'm going to get 4 equivalent orbitals. And the 4 equivalent orbitals are going to kind of look like an S and kind of look like a P. They kind of look like a P because they have these kind of lobes. So this is one of them. This is another one of them. This is another one of them. And this would be the last one here. And so these are called hybrid atomic orbitals. And the hybrid atomic orbitals are to minimize repulsion. They minimize repulsion by maximizing the distance between it. And so you might have seen these with balloons or something like that. And so here we have the nucleus. So we'll have one sp3 orbital up here. We'll have another sp3 orbital here. And another one here. And a fourth one here. And so we get 4 equivalent sp3 orbitals. And so that tweaks the atomic orbital energy level diagram. And so the atomic orbital energy level diagram is going to look like this. So originally what we did was we promoted 1 electron to maximize bonding. So we started off with 2 in the S and then only 2 in the P's. So we started off with something like this, and then we promoted so that we could get 4 bonds. But the 4 bonds would have weird bond angles and wouldn't minimize repulsion. So we end up with now new orbitals, which are trying to minimize the repulsion. So we end up with something like this. And so carbon's going to have 4 valence orbitals like this, and then we could put the valence electron in those. So we'll have an sp3 electron here, an sp3 electron here, and sp3 here. And in this way, a hydrogen can come along and bond to this. So let's put the hydrogen up here. The hydrogen has an s orbital with 1 electron. And we'll form a bond there. Now the chlorines, we don't have to hybridize, or we can hybridize if we want. But the chlorine's going to come in here. I'll just show. They come in here. Some books hybridize it, some books don't. If we don't hybridize it, then this is a 3p. And it bonds here. I'm just going to show the 3p. All the other orbitals are filled. Or we could hybridize it. And the 3p are going to have two lobes. Actually, more than two lobes because there's nodes there. We have cone nodes and conical nodes and planar nodes. And those come in here to bond.
Do you do that with like a darker mark?
Okay. Let's do this with a darker color here. So the chlorine comes along, and this is the 3p. Okay, is that
Yeah.
visible? For chlorine, we might hybridize, or this would be unhybridized. We can hybridize this one too. But it depends on the author of the book. You know, some books will not hybridize these, other books will hybridize it. For chlorine, we could have hybridized it. So, what would it look like if we hybridized the chlorine orbitals as well? And that's to minimize the repulsion. So, when we look at chlorine, chlorine's going to have third shell, like this. So when we look at the repulsions between these two lone pairs, the repulsions will be at 90 degrees. Although we can't pinpoint where the electrons are, effectively it's a 90-degree repulsion. We can make that a 109 repulsion by hybridizing it. And so rather than having a 90-degree repulsion between this pair of 2p x and this pair of 2p y, we can make it a 109. And if we make it a 109, then the energy is going to be closer to the p because it's 3/4 p. It's only 1/4, so the energy is going to be 3/4 the way up to the p. Here. And then we put the three lone pairs here. When we put the three lone pairs here, then that will minimize the repulsion. So rather than having a 90, we're going to have a 109 repulsion here. And so that means these would be sp3s here as well. We're going to have 4 sp3s. And so if we were to redo this here, then we'll have the chlorine here, but rather than the chlorine P, we'll put a chlorine sp3. Oops. To the carbon here. And then we're going to have 3 more orbitals with lone pairs. And the 3 more orbitals with lone pairs are going to maximize the distance separating the lone pairs by hybridizing it in a tetrahedral arrangement. Whereas over here, if we left this as unhybridized P, then there's going to be another unhybridized P here with the lone pair. And so we're going to see a 90 repulsion there, and then there's going to be one more unhybridized P here that sticks out with a lone pair. And so we have PX, PY, PZ, and those are going to have 90s. Do you see that? Versus this, where we can kind of spread them out if we decide to hybridize it. Now, we don't decide, the atom decides. And so what happens is this: the smaller the atom, the more hybridization is important. The bigger the atom, the less hybridization is important. So if we're comparing, let's say, fluorine versus chlorine, fluorine for sure, you better hybridize it. Because fluorine's a small atom. Small atom, the electrons are bunched up. Right? Chlorine's a much bigger atom. There's a lot more room. So maybe there's so much room, you know, we don't really care if it's a 90 or 109. It doesn't make that big of a difference, right, for a big atom. If we went to bromine, then bromine we might not hybridize at all. We might not hybridize at all because it's so big. There's lots of space. There's lots of space, it doesn't really matter. 90, 109 makes very little difference. And so the smaller the atom, the more important hybridization is. So for example, carbon, yes, we always hybridize carbon. Silicon, yeah, okay, maybe. Germanium, probably not. You know, it's so big. Does that make sense? And so hybridization is due to repulsions and trying to minimize. So for chlorine, I usually hybridize this.
How do we know when to hybridize and when not?
We look at the angles. The angles will tell us. And so what we do is, I don't know. And so we measure the angles and then see. Are the angles telling us it's hybridized or not? And so let me give you a classic example here of this. H2O versus H2S. The HOH angle here is, about 109 degrees. It's actually closer to 105 because of distortion. However, the H2S, the HSH angle here is about 90 degrees. So this tells me that oxygen here is hybridized because of the angle, but sulfur is not. And so this is a combination of observation plus theory.
Okay, so if it's not hybridized, it follows the model of just.
Right. And so when we look at the orbital energy level diagrams for oxygen versus sulfur, we write it different. So oxygen would have 2s and the 2 p's hybridizing to make 4 sp3s. I should have. So the 4 sp3s, I'm just going to overlay it. 1, 2, 3, 4.
I forgot, but what is
3 parts P, 1 part S. There's actually 2 sp3 because it comes from n equals 2. Where sulfur is in the next shell, and so that's going to be 3s. And so over here, sulfur, actually, how many electrons do we have for oxygen? For valence electrons, we have none. 6. So 1, 2, 3, 4, 5, 6. So we can form 2 bonds. For H2S, we have 3s and we have 3p here. And it also has 6 valence electrons. This is in the same family. But it looks like this. Now, if the p orbitals form the bonds here, then the p orbitals are 90 degrees. Whereas if the sp3 orbitals here form the bonds, then the angle is going to be closer to 109 degrees.
So when it's hybridized, it always has this type of bond.
Yeah, right. But it gets a little bit more complicated because we're picturing it. And so rather than this is a fixed percentage. When I see sp3, it's 1 part S, 3 parts P. So sp3 means it's 25% S and 75% P, right? But in reality, sometimes we don't have clean numbers like that. And so in reality, we just look at it as a continuous. It's not like quantized, it's kind of continuous. In other words, what we could have is we could have like 80% P, 90% P, depending on how much it has to hybridize. So we could have different percentages of character, of S and P character. But we have certain hybridization schemes that we do. And so this is one of the things we're going to be looking at. And since this requires some practice, I wanted to combine. So this is what I mean by modified. I want to combine this atomic orbital stuff with Lewis structures so we get more practice drawing out these atomic orbitals and then picturing them. And so this is what we're going to do in addition to the Lewis structures. So let's take a look at another example here. Okay, we're going to look at NF3 next. So the first thing is, how many valence electrons does nitrogen have? 5 valence electrons. But what I want to do is I want to draw the entire atomic orbital energy level diagram. So if we draw the whole thing, which orbital do we start with? 1s, and there's going to be 2. And then we're going to go to 2s, and then there's going to be 2. And then 2p. So we need 5 electrons in the outer shell. The outer shell is the second period here. So that's 1, 2, 3, 4, 5. So when I look at nitrogen, how many bonds could it form? 3 with these half-filled P's. Is nitrogen a big atom or a small atom? Pretty small atom. So there's going to be repulsion between the lone pair and the bonding pairs. And so what's going to happen here is the fluorines are going to come in, and they're going to bond to the nitrogen. So one fluorine is going to come here and bond here. Another fluorine is going to come here and bond here until we can form 3. Here we don't have to promote. I mean, if we promoted, we still can only form 3 bonds. And so there's no reason to promote. But since this is a small atom, if I left these in the P, what would the angle be? The the FNNF angle. 90 degrees. But we know that ammonia, this is nitrogen trifluoride, has, do you guys remember Vesper? Maybe I'm jumping too far ahead, but I want to do everything at once. The angle's not 90 degrees. Do you know what the angle is? 109, or close to it. It's like 107, but close. The actual shape of this is what we call trigonal pyramidal. And the bond angle here is very close to 109. And so the FNF angle is about 109 degrees. It's actually 107, but 109, which tells me that these orbitals must be hybrid. And so what I'm going to do is I'm going to take 1s and 3 p's and make 4 hybrid orbitals. And each of those hybrid orbitals are going to be 1 part s, 3 parts p, so I'm going to call them sp3. 1 part s, 3 parts p, 1 part s, 3 parts p, 1. In other words, 1s and 3 p's are going to combine to form 4 identical sp3 orbitals. And those 4 identical sp3 orbitals are going to be oriented on nitrogen in a tetrahedral arrangement. So one sp3 orbital is up here, another is here, and then one sticks out over here, and one sticks in. And so I get 4 equivalent sp3 orbitals, and in order to maximize the 3-dimensional distance between these, they're all at 109.5 degree angle with respect to each other. And then I'm going to put all my valence electrons in there. So I got 1, 2, 3, 4, 5 valence electrons. So one of these orbitals will have a pair. That's a lone pair. And then another will be a single, another will be a single, and another will be a single here. And that means fluorine can come in. So let's take a look at fluorine. So fluorine, okay, nitrogen has fewer protons than fluorine. Nitrogen has 7 protons, 7 electrons, 7 protons. Fluorine has 9. 9 electrons, 9 protons. So the 1s orbital should be lower in energy, higher in energy, or the same? Lower. So fluorine's 1s orbital is going to be lower in energy, and the 1s orbital is going to be bigger or smaller? Smaller, but it's all right. We're not going to. And so we're going to have 1s, 2, and then 2s, 2, and then 2p, 1, 2, 3, 4, 5, 2p5. In other words, we're going to have 7 valence electrons here. Now, fluorine is a small atom or big atom? It's very small. And there's going to be repulsions between these. To minimize the repulsions between the valence electrons, we're going to hybridize it into, right, sp3 hybrid orbitals. And those sp3 orbitals, we're going to put our 7 valence electrons in here. 1, 2, 3, 4, 5, 6, 7. And this is going to leave me with one potential bond here. And so what's going to happen is the fluorine is going to come here and bond. I just have to flip this electron upside down, but it's no big deal. Upside down, right side up, it doesn't matter. So fluorine comes in there. And so that means fluorine is going to come in here with its own sp3s. Its sp3s are going to be a little bit smaller than nitrogen's, right?
Yeah.
Because Z is higher. Z and Z effective are higher. What was Z? Z is the nuclear charge. What's Z effective? The nuclear charge fell by the outermost electron due to shielding. And so Z effective is going to be less than Z because of shielding. And so the fluorine's sp3 is going to come in here, and we got 1 electron there. The other sp3s are already filled. So we got 1 sp3 here, another sp3 we're going to put out. This is sticking out, so I'm trying to shadow it. And then I'm going to dot this one, which is sticking in. And so to minimize the repulsion between the lone pairs and the bonding pair, we adopt a 109 angle. The only way I can get that 109 angle is by hybridizing. And we hybridize to minimize repulsion. Okay, so I'm going to be able to fit how many fluorines around here? Okay, this fluorine is going to come in here with the sp3 bond here, and this fluorine is going to come in here with an sp3 and bond here. I'm not going to show the other orbitals because it's going to get cluttered. Yeah. Yes. Yeah.
Our beautiful nitrogen trifluoride. Does the single bonds present and then the single bonds plus an open bond, or an open pair on the nitrogen, change the shape at all?
Yeah.
Okay.
Yeah. The lone pair, if that lone pair wasn't there, then it would be a totally different shape.
Okay.
Yeah. Okay, the next molecule that we're looking at is not a molecule, it's an ion.
Okay.
And the next species we're looking at is BF4 minus. The minus means that there's an extra electron. And so let's first look at boron. Boron has how many electrons? 5 total electrons? Okay, so boron has 5 electrons. The first electron is going to go in there, 1s. And then the next electron will go in the 2s. That takes up 2. And then 1 more electron is going to go into the 2p. Okay, in this configuration, how many bonds can boron make? Only 1. Only 1. So if boron can only make 1 bond, then it's not that stable. And so what we can do here is we can do what? We can
Maximize bonding.
maximize bonding by promoting the s electron to the p. This is not ground state, right? This is not the lowest energy. Ground state would be paired here. And so if I have a single boron, then the single boron is not going to be happy like this. But this is not a single boron because this boron is going to bond. And so how many fluorines should this boron bond to? 3. And so this boron should bond to 3. fluorine. One fluorine comes here and bonds here and here. But do you see this empty orbital? This empty orbital, well, we can't make a bond there unless we have an extra electron. Do we have an extra electron? We have an extra electron. And that is, boron doesn't have 5 electrons here. Boron is going to have 6 electrons here because we are going to have this extra electron here. And that extra electron is going to mean we can form one more bond. And forming one more bond is always better if it's in the same shell. Now, how does boron end up with that 6 electrons? Well, let's take a look at the Lewis structure first. So when we look at the Lewis structure for Bf4 minus, the Lewis structure looks like this. The Lewis structure doesn't have to mimic the shape. And the shape is not square planar like this. And this whole thing carries a negative charge. What atom is that extra electron on? Well, we'd expect the extra electron to go to fluorine, but it doesn't because fluorine's happy. This is formal charge. So the formal charge of fluorine are all 0. They don't want any extra electrons because they have 8 electrons, which fills their valence shell. Who has the extra electron? Boron. Boron has the extra electron. It has a negative formal charge. Boron should have only 3 valence electrons. Boron has 4 valence electrons here. And so with that extra electron, we can make a 4th bond. But, okay, so number 1, we promoted an electron to get an extra bond. And not only do we promote an electron to get an extra bond, we add an extra electron to make a 4th bond. Okay, the next thing is boron's a small atom. And so are they going to be happy at 90-degree angles? No, not if they can spread out. And they can spread out if we do what? Hybridize it. And so this is going to hybridize to 109. So basically, we're going to take this S and the P's and make them all equal. When they're equal, they aren't midway. They're going to be 3/4 closer to the P than the S. And then we'll have our hybrid sp3 orbitals here. And then we'll just fill these in with the electrons here. And that's just to maximize the distance, minimize the repulsions. Does that make sense?
Yes.
And so for boron, the atomic orbital energy level diagram that I write is going to be like this. Boron's going to be 1s, yes, that's no problem, that stays the same. However, there's no more 2s. There's going to be a 2sp3 here, and then there's no more 2p's. There's going to be 2sp3 here, a 2sp3 here, and a 2sp3 here. And so there's no more s, and there's no more 2p's. And so now we have 4 equivalent orbitals. And then we'll just put in 1 electron here, 1 electron here, 1 electron here. So what we've done is we've maximized the bonding, and we've minimized the repulsion. So fluorine comes in here, 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 and here. Does that make sense? So the Lewis structure looks like this. However, that doesn't really show its shape. What's the shape of boron tetrafluoride?
Tetrahedral.
It's tetrahedral. And so to show it as tetrahedral, we draw with dashes and wedges. Formal charges we usually circle, and boron's going to have a negative charge, so we can just circle it like this. So this would be the anion. They give it a different name.
when you're drawing the structure in the proper shape, the wedge is protruding outwards and the gas is protruding
Inwards, yeah, from the board.
So I've never seen a wedge or a gash in a structure.
Oh, you haven't?
Okay.
Well, that's what it means.
Yeah, we never got that far. No, we did. We never got to wedges and gashes. He just made us draw it like if it was 2D.
Wait, wedges and what?
Wedges and gashes.
Dash.
Gashes. Yeah, gashes. You know, like
Yeah, like dash.
yeah, no.
Dash line.
Yeah, no, and Chem before, we never did that. We literally did it 2D for everything. That's how we had to do it.
Yeah, I was all.
It's how we did the, we actually did those too.
I thought that's what we were doing. I see you too.
You know, because for our final science, we never used wedges or gashes to really show the structure. We had to do it all 2D.
That's crazy. So you never learned how to body
We did, which is the interesting part, but we never learned that you could write it that way.
How did you learn how bonding was? Yeah, how did you even do that?
He never showed that.
For simple Lewis structures, we could use the Lewis dot. We don't have to follow the rules. Or we could follow the rules. For Lewis dot, let's draw the oxygen in a different color here. How many bonds can each oxygen make? 2. And carbon can make 4. And so if we throw in an oxygen here, we can make 1 bond here. And then we throw another oxygen here, we can make 1 bond here. But the oxygens are going to want to make 1 more bond. And the carbon's going to want to make 2 more bonds. And so what we'll do is we'll make a double bond here. And here. And so we end up sharing 2 pairs of electrons. There are different ways we can do this. So we end up with a Lewis structure that looks like this. So this is going to be modified. Now, what we did earlier was we looked at carbon, and carbon was 1s, 2, 2s, 2, 2p, 2. Like so. And so it looks like in this case, we want to promote and maximize the bonding. So we promote and maximize the bonding. So we have 1s, 2, 2s, 1, 2p, 3. So how many bonds can form here? 4 total bonds. But can we have 4 sp3 orbitals here at 109 angles?
No, there's only 2 bonds.
There's only 2 double bonds, and those 2 double bonds are, do you know the angle here? The angle here is 180 degrees. At 180, what's the bond angle for 100? For the tetrahedral sp3s? 109. And in fact, when I look at the p's, the bond angle here should be 90, not 180, because a p orbital is going to have a lobe here and a lobe here. And when we form 1 bond with a p, it's either on the top lobe or it's on the bottom lobe, but it can't be on both. Because if I bring 2 atoms in here, that would be like trying to form 2 bonds to the same orbital. So if I bring a hydrogen here and a second hydrogen here to bond to the same p orbital, is that possible? No, that would violate the Pauli exclusion principle. And so the p orbital can only sustain. So there's no way we can bond 180. There's no way. And so we're going to do this. The type of hybridization we have depends on the shape. So these are the shapes. If we have a linear shape, then the hybridization is what we call SP. If we have a trigonal planar shape, then the hybridization is SP2. If we have a tetrahedral shape, then the hybridization is SP3. We have more shapes. The additional shapes would be trigonal bipyramidal. In trigonal bipyramidal, its hybridization is SP3D. And one more shape is octahedral. In octahedral, the shape gives us an SP3D2 hybridization. Now the SP3D and the SP3D2 are currently being rethought. And there is an alternate picture that we'll talk about later. Alternate picture to replace the hybrids, these hybrids. So anyway, but these ones are not being rethought. These ones are pretty well and good. And so what we needed to do is we need to see it's linear. Well, this is linear. And this comes from Vesper. Does anybody remember what Vesper stands for? Vesper stands for valence shell electron pair repulsions. We just want to minimize. So if we have two double bonds, the two double bonds want to spread out as far apart from each other as possible. And the furthest they can get away from each other is at 180 degree or linear configuration. And so that means it's linear, that means it's SP. And if it's SP, we grab one S and one of the P's, like this. So if we grab just one S and one of the P's, then we form what are called SP hybrids. And the SP hybrids are going to look like this. They're going to be one part S, one part P. So it's 50-50. 50% S, 50% P. So they'll just be midway between. And then the original P's are still here. These are called unhybridized P's. So we lost one of the P orbitals. We lost one of the P orbitals to form these hybrids here. And when we look at these, we'll have our 4 valence electrons like so. Now the SP orbitals are going to be at 180 degree orientation. So one SP orbital sticks out on this side. This is a small lobe. So this would be the positive and this would be the negative. The other SP is going to stick out this way. And so it's just different orientation. So when I look at the carbon, it looks like a p orbital, but it's not. A p orbital would have 2 lobes and be the same orbital. These are 2 separate orbitals. These are 2 sp orbitals. And so now we can bond things 180. So if an oxygen comes along here, it can bond. here, and another oxygen can come on here and bond here. And so it's at 180. Now, the funny thing with oxygen is oxygen's going to come in here and bond here. But this oxygen's also going to come in here and bond here into one of the unhybridized. So each oxygen is going to bond to two different orbitals. An sp orbital and a p orbital here. And the second oxygen is going to come in here and bond to this sp and this p. And so we're going to generate a different kind of picture for this. So the different picture for this is going to look like this. And so what I'm going to do is I'm going to try to draw the orbitals on these. But before I do that, I shouldn't have erased the CO2. The CO2 looks like this. This is linear. However, when I look at the oxygens will have a group here, a group here, a group here. If I have three groups like this, what configuration, what geometry, what shape will minimize the repulsions between these three? Trigonal planar. So this is trigonal planar. If it's trigonal planar, that tells me that the hybridization on that oxygen, because oxygen is a small atom, must be sp2. And so let's take a look at oxygen's normal orbital energy level diagram. And so oxygen's normal orbital energy diagram is a 1s, 2 electrons, a 2s, 2, and a 2p with 4 electrons. And so we don't really have to promote, we're going to form 2 bonds here, nonetheless. But when I look at this, I want to minimize the repulsions between these groups. To minimize the repulsions between these groups, I'm going to take 1s and how many p's? 2. Yeah, so I'm going to take 1s and 2 of the p's. And then I'm going to form 3 equivalent orbitals. Those 3 equivalent orbitals will each be called an sp2 orbital. And so I'll get 3 equivalent orbitals, which are going to contain 2 parts p, 1 part s character. And these are all sp2 orbitals. But that leaves 1 p orbital untouched. And that 1 p orbital is over here. And when I look at these orbitals here, I'm going to have 2 lone pairs and 2 singles here. So when I look at oxygen, well, what do these sp2 orbitals look like? The sp2 orbitals are going to be in a trigonal planar arrangement. And so when I look at oxygen, I'm going to have sp2 here, an sp2 here, and an sp2 here. That gives me my trigonal planar arrangement. And what about the p orbital? The p orbital is actually perpendicular to the plane. So one lobe of the p orbital sticks out, the other lobe sticks in. So this is my unhybridized p orbital here. And then I'm going to have 2 lone pairs. And so one of these sp2s is going to be filled. This sp2 will be filled. This sp2 will have a single electron and can bond. The p orbital will have a single electron and it can bond. All right, what I'm going to do is I'm going to grab it by this orbital and rotate it. So if I grab it by that orbital and rotate it, this sp2 orbital is in the same relative position. But what happens is it puts the p orbital in profile. So the p orbital, one of the lobes is going to be up and one is going to be down. So that's going to be my p orbital there. And this sp2 orbital is going to stick out like this. And so I'll have an sp2 orbital here. And then I'm going to dash in an sp2 orbital here. And so I'll have an sp2 orbital here. These 2 sp2 orbitals will have lone pairs, so they're filled. But the p orbital has a single electron in it. And this sp2 orbital will have a single electron in it. And so this is the valence. I'm ignoring the 1s. The 1s is still there. And nothing's happening with 1s, so I'm not even going to show the 1s. This is the core. electrons. But this is what's happening with the sp2p in the valence shell. Okay, so for carbon, let's do the same over here for carbon. For carbon, I had sp hybridization. So I have carbon here. Now, one sp orbital is over here. Okay, that's going to have a single electron here. And then another sp orbital is 180. And that's also going to have a single electron. But I'm going to have two p orbitals. One p orbital is just flat in the page. And so this will be my py, let's say. And then one p orbital is going to kind of stick out and stick in. This will be the p, let's say z or the p. Yeah, we'll just call it pz. Okay. And each of these p orbitals will have one electron, like this. And so what we're going to do is we're going to bring everything together. And so to this single oxygen, a carbon comes in, and it's going to bond here and here. And to the other oxygen, a carbon, the same carbon will come in and bond. And so when we put this together, this is it. We're going to put the carbon here, an sp orbital here, and this sp orbital here will bond to an oxygen sp2 orbital here. And so we'll form one bond here, like that. But this carbon also has a p orbital. Actually, I should have done this. This carbon also has a p orbital here that has one electron. And this oxygen also has a p orbital with one electron. We'll put its spin down. And these are the 95% probability boundaries, but you see there's some overlap here in here because these orbitals can extend further out. I just drew them compact. But we'll form this. These two overlaps is considered one bond. Because we have one p orbital and another p orbital coming together. And so this is not four p orbitals coming together, it's one p orbital coming together with another, so that makes one bond. And so this is what we call a double bond. In this case, this double bond comes from the pp overlap, which forms a bond, and the sp2. And so this is a double bond. Now the oxygen is going to have two lone pairs in sp2. So there's going to be one sp2 sticking out here with a lone pair, and one sp2 sticking in here with a lone pair. So that's my two lone pairs here. And then there's going to be another oxygen over here. And then this carbon is going to have another sp orbital here. And this oxygen sp2 orbital is going to come in here. And so we're going to form another bond to the carbon here to oxygen. So this is what we call an sp2-sp bond. And then there's going to be a lone pair in this other sp2 orbital and another lone pair in this sp2 orbital here. So this one sticks out, this one sticks in. However, the orientation's wrong, because if I try to orient it like this, it can't overlap here. That's violating the Pauli exclusion. I'm going to have too many electrons. So what I have to do is I have to take this whole thing and then rotate it like this, 90 degrees. And so this is the wrong orientation for this. And so what I'm going to have to do with the second oxygen is this. And so let me redraw the left-hand portion of this. If I reach over the left-hand portion of this, it's going to be like this. This p orbital is already taken with this oxygen over here. And so what I'm going to do is I'm going to have to take the pz on the carbon. And there's one more. And so this p orbital is already taken, but I have one more p. That one more p is going to be oriented perpendicular to this page. So we'll just call it the pz one here. And this is going to have one electron in it. And then there's going to be a lobe behind there. So we're going to have one more p orbital that's kind of sticking out like this. This is called the pz. Let's say this is the py here. And so what I'm going to have to do is I'm going to have to rotate the oxygen so its p lines up. And so this oxygen over here, I'm going to rotate it so the p orbital lines up like this. What that's going to do is sp2 is going to be the same. So sp2 will match up with the sp over here. So this is sp2 sp. And then another sp2 here is going to be sticking out with a lone pair. And another sp2 is going to be sticking out with a lone pair here. But now the pz on oxygen will match here. And so, in other words, it's like this. I have a p orbital here in the plane p orbital here. So these two p orbitals match. And then I have a p orbital sticking out and a p orbital here sticking out. And these two are matched. And so they're one is oriented like this with a p sticking out. And this oxygen is oriented like this with a p vertically. Does that make sense? And so what I have are a double bond here. And so the double bond here is this bond and this bond. That counts as a double bond. And the same thing with the oxygen over here. And we're out of time. So I guess we didn't get to it. But this is kind of what we're going to be doing with our lab. So we're just going to get practice with orbitals and hybridization and this kind of stuff.